Any questions about anything? Wait, is there a lab this week? I think there is. Yeah, there is a lab this week. Yep. Yep. Any other questions? Not a formal one that I'm doing, but if the TAs get all energetic and stuff, you might have a surprise one. I think what I'm going to do is maybe one of the days next week in lecture, the post-break time, I'll just throw the floor open to questions, and I'll warn you so you can come prepared, because I'm not going to start reviewing stuff. I'm just going to stand here and wait for you to ask me something. So yeah, that's what I'll probably do. Yeah.
You said everything for all material was covered last Thursday. That was the end of 311.
Yeah. Okay. And that lecture, Alex and I will get that lecture up on the video on the YouTube site in time for you to look at it if you want. And some blurbs are missing from the latest lectures. I haven't put little thumbnail descriptions of what's going on in them yet, but I will. Any other questions? And I sent an email last night. I just want to say it out loud too. I need to know all the special accommodation things like direct conflicts, SDS letters, whatever. I need to see that stuff as soon as possible because I have to schedule rooms and line up TAs and all that stuff. So please make sure I'm not hearing next Wednesday that you have a direct conflict with your OS class or something, that night. Just makes life easier for all of us. Okay, so anyway, so last time we kind of wrapped up the material essentially through chapter 4 of the book. And what we've been doing for the vast bulk of the time so far is talking about signals. Okay? So we've been talking about signals, and we've talked minimally about systems. And so now what we're going to do is we're going to talk about systems. Okay, so far it's mostly, quote unquote, all about signals. Now we're going to talk about systems. And you'll notice that the title of the book, or the title of the chapter, chapter 5, is FIR filters. They call them FIR filters. I'm going to call them FIR systems. Now, you can view them as filters, and when we get into the discussion of frequency response and that and related topics later on, you'll see why they call them filters. But really, I just like to think of them as examples of discrete time input-output systems. And you might remember from the first week of school, I said, what is a system broadly speaking? So this is just something that you've seen before. A system, and here we're talking, by the way, about discrete time systems. Everything's in discrete time. A discrete time system is just an entity, whatever that means, that quote unquote processes input signals into output signal. So often I'll represent it like this, like it's like a box that takes some input signal x of n and output signal y of n comes out. And again, this notation is a little deceptive because what it looks like in this picture is that for each n, y of n at that particular time n depends only on the value of x at that particular time n. But really, this picture is whole signal in, whole signal out. Okay, so caution. Remember that this picture represents whole signal going into the box and whole signal coming out of the box. So in particular, for each n, the value of y of n, that is to say the value of this whole signal output at time n, depends in general on all the values of this whole input signal x that goes in. So all the values x of m, not just on x of that specific time n. Okay, so whole signal in, whole signal out. And as it happens, FIR systems are systems that put a restriction on how much of the input signal the output depends on at each time n, as we will see. But in general, y of n is allowed to depend on the whole history and future of the input signal x of n. All right, so what are some simple examples? We're going to carry these examples along, and some of these are going to be FIR systems, and one of them is not. Okay, so some examples, some example systems. And the first ones are going to be essentially trivial examples. So what's the most trivial thing you can think of a system doing to an input signal? Don't give it away. Yes.
Nothing.
So that the input goes in and it comes out just the same?
Yeah.
OK, that's a really good example. What's your name, by the way?
Jade.
Jade? OK. So this is one really kind of trivial system, what we call the identity system. OK? The identity system is one for which you put x of n into the system, and what comes out is y of n equals just x of n for all n. And that's true for every input signal. Now, if you think circuitsy kind of thoughts, right, like you can think of a box where you have like two wires leading up to two terminals, and you hook up a battery or voltage source across those terminals, and you measure the voltage source across the terminals, and what are you going to get? You're going to get the voltage on the battery. So that's like an identity system. What's the flip side of the identity system? Think about circuits. Yeah.
Like the negation of
A negation of it. That's well. That's true. Well, think about it. Open circuit is identity. Yeah, short circuit is your name Brendan? Is that right? Okay, because I met you one day over at Tegel, right? That's okay. Yes, I'm trying to remember everyone's names that I know. Okay. Anyway, okay. How about the zero system? That's the one I was thinking of. The zero system is the thing that takes every input signal x of n and gives you y of n equals the zero signal. The zero signal is a perfectly valid signal. Remember, we talked about signals, the trivial examples of signals. This is for every input signal x of n. So the system that does nothing, the identity system, and the system that kills, annihilates, the zero system, those are in some sense the most trivial kinds of discrete time systems I can think of, right? Now there's others. There's levels up, like negating, like a system that takes every input signal x of n and just flips it, right? Like an inverter, like an op-amp inverter. If you think about that in discrete time, that would be an example of a pretty simple system. All right, so those are systems. Now another system that's slightly less trivial is what I call the pure N1 shift system. Okay, so what is the pure N1 shift system? N1 is some given integer. And this system takes every input signal x of n and processes it into output y of n, which is just x of n shifted by n1. And that's for every input signal. These systems come up all the time. Input goes in, gets shifted by N1 to give you the output. If N1 is positive, it's like a delay. So you can think of this being a time delay of length N1 in taking x of n to y of n. All right, but anyway, that's another system, and that's a perfectly good system. Okay, here's another one. An averager system. And I'm going to write a specific kind of averager. It goes like this. Cap m bigger than 0 is a given integer. And let's make it m bigger than or equal to 0, because we're going to have an m plus 1 here. And what the system does is, for every input signal x of n, what is the output signal y of n going to be? Y of n for each n y of n equals this 1 over m plus 1 times the sum from k equals 0 to m of x of n minus k, i.e., for at each time n, the value of the output signal y of n is the average of the previous cap m plus 1 values of the input signal, including the value at time n. Okay? So that's an averager system. Those come up all the time. One final example is something I'll call the Discrete-Time Integrator. System. And what's that system? That system, it takes input signals x of n into output signals y of n. And for each n, y of n is going to be the sum from k equals 0 to infinity of x of n minus k. That is to say, for each time n, the value of the output is the sum of all the previous values of the input, including the one at time n. And if you think about it, the first three examples, well, there's really 4, if you count the identity and 0 as 2 different examples. Every input signal x of n is fine for those systems. You can take someone come up to you in Hall Plaza and give you an arbitrary input signal x of n. You can put it through any of these systems up to here and get a well-defined output signal. Not so for the discrete-time integrator. How come? Think about it. Like, for y of n to be a signal, a well-defined signal, this sum has got to converge. So if I put in, say, a constant signal, x of n, where the constant is non-zero, say x of n equals 3 for all n, y of n is not going to be well-defined. So this raises a cautionary thing for us. So caution, unlike the previous examples, not every input signal x of n is quote unquote admissible for this system, the discrete time integrator. We have to have some condition on the input signal to make sure that it's OK to sum it from minus infinity to n and get a number every time. But all those are easy to describe examples of input-output discrete time systems. And the first three are examples of what we call FIR systems. So the first three, the examples other than the integrator. So examples, just so I don't have to keep saying, is it 3 or is it 4? Okay. So examples other than integrator are what we call FIR systems. And by the way, don't go saying FIR systems. Okay? No one's going to know what you're talking about. And then if they discover that you meant FIR, they will think you're like a total ignoramus about systems. Everyone says FIR, no one says FIR. Okay? It's not like NASA, or like if you said, "Oh, I'm going to go work for NASA," no, everyone would go chuckle. They don't know how to say NASA. But if you say FIR systems, people will go, face palm. Who am I talking to? A hotelier? Or what? No. Anyway, just kidding. I don't know whether I know there was a government major here the first day. I don't know if there are any hoteliers around, right? Is the government major still here?
He had no class. He was never in the class.
He was never. He had no class, so he just came for fun. Oh.
So he showed up, and he's like, "Yeah, he might be here on Thursday.
Yeah.
Class on Tuesday or Thursday."
Speaking of noticing I told Patty Gagne, the building manager, about all the broken chairs in the front row, and she wrote herself a note. I see you're sitting on an upside down. Yeah. Anyway. Yeah. All right. So these are examples of FIR systems. Now, in a minute, well, not a minute, like maybe in 45 minutes, I'm going to tell you why they're called that. Okay. So we'll discuss the name later and why we call them that. But for now, I'm going to write down a general form of the I/O relationship for what is called a causal FIR system, which is what we're going to devote the bulk of our attention to. So for now, what we're going to do is we're going to focus on what are called causal, and more on this word later as well, FIR systems. All right, now what is the general form of the I/O relationship for one of these? So it looks like this. For each n, y of n, the value of y at the time n is going to be a sum that looks like this. The sum from k equals 0 to cap m of bk x of n minus k, where the bk's are just numbers. And generally, we're going to be talking about real numbers. And there's names for the BKs. Like I can just say the FIR system with those coefficients. I'll be talking about the BKs. Another word that people use and especially old school types, they call BK the taps of the FIR system. Has anyone ever heard filter taps, that phrase, seen it? Where have you seen it, Alex?
So I was just brushing up yesterday on my digital systems, and there's this Python library where you can put in some specifications, and you can get a bandpass FIR filter,
Mhm.
and one of the arguments is n, which is the number of taps.
Number of taps. Okay. Why do they call them taps? Do you know? Do you know why they call them taps?
Because you can tap delay lines.
Yes, exactly. There's a famous, one way of talking about FIR, causal FIR systems is tap delay lines. And whenever I say that phrase, in my head I hear it with a southern accent. Okay, because there's a professor in our department, Rick Johnson, who's actually close to retiring. He's on phased retirement right now, but he's a systems type as well. And he's from Georgia. He's from Macon, Georgia, and he has this real preacher kind of voice, you know. And he's always talking about FIR systems and tap delay lines and things like that, you know. So when I see here tap delay line, you visualize the signal x of n going in, and these little taps on the line with weights on the taps being the BKs, measuring the x at intervals. That's why they're called taps. But anyway, this is the general form of the I/O relationship for a causal FIR system. And a minute ago I told you that the examples that we talked about other than the integrator are FIR. Let's make sure we buy that. What do we have to do? We have to take those examples and figure out what the BKs are and what the M is for them. Okay, so let's recast the examples above in this general form. Okay, the zero system. You could do this any number of ways. So the zero system, the answer is non-unique. But just to be perverse, how about I'm going to say set m equal to 19 and bk equal to 0 for all k between 0 and 19. Okay? That's one way to implement the zero system. It's a 19-fold tap delay line with all the taps being 0. You could also let m equal 0 and by convention regard the empty sum as, well, no, you would still have to have b0. So you could also have b0 equal to 0. So or m equals 0 and b0, the only relevant b equals 0. That's another way to do it. Okay, the identity system. I'm going to let m equal 0 and b0 equals 1. And that will just take input x of n and put out the same signal as the output. Because you look at this I/O relationship here, m equals 0, so you've got exactly one term in the series, the k equals 0 term. The k equals 0 term is b0 times x of n minus 0, which is b0 x of n. b0 is 1, y of n equals x of n. Boom. All right. Averager system. Oh, pure n1 shift is the next one. And for this one, I'm going to assume that n1 is bigger than, say, bigger than 0 for now. If it's equal to 0, then it's just the identity system. How about this? How about m equals n1 and b0 equals 0, b1 equals 0, and so on. bk equals 0 for 0 less than or equal to k less than m, and b sub cap m equals 1. Now, why does that work as specification for the pure n1 shift? Let's plug it in. Let's see what happens. So check. Y of n has to equal the sum from k equals 0 to m, bk x of n minus k, and that's going to be equal to the sum from k equals 0 to n1, because I'm setting m equal to n1, of bk x of n minus k. And that is going to be a bunch of zeros until you get out to k equals n1. So it's going to be 0 plus 0 plus dot 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 plus 0 plus 1 times x of n minus n1. And therefore, y of n is x of n minus n1 for all n. And that's what we wanted to implement. OK. Now that you've all seen these, seen the kind of sleight of hand that one does to turn a kind of intuitive description of what's going on in the system into one of those equations, I want you to do the averager for me. So how about the averager? Now, this one is kind of like it's easier than it looks because I actually kind of gave you the averager in the BK form already. So tell me what, for the averager, what is m for the averager? This is a trick question, sort of. It's just m in the way I described it. You know, if I wanted to, I could have described it with an L to begin with, but I didn't do that on purpose because I didn't want you to get all confused. So for the m, it's just m. Whatever that means. I don't want anybody from the math department to walk in and see that. You know, that would be bad publicity for ECE. What about the BKs? Yes.
Shouldn't it just be 1 by n plus 1?
Yes, but for k between, so bk is equal to 1 over m plus 1 for what range of k values?
0 and n.
Yeah, 0 less than or equal to k, less than or equal to m. Because the averager is just this. Y of n equals 1 over m plus 1, sum from k equals 0 to m, x of n minus k. And if you write that out and term-wise, it's just 1 over m plus 1, x of n, plus 1 over m plus 1, x of n minus 1, plus dot 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 plus 1 over m plus 1, x of n minus m. Boom. So all the BKs are the same. And what's your name, by the way?
Apu.
Apu, OK. Anyway, there we go. So that's recasting the FIR ones of the examples in terms of the BK notation. Now, an important thing to look at here is pictorially what's going on with an FIR system. And this is a really important thing to process and a habit of thought that you want to develop. And that is the following. So observe that any FIR system, and you know, there's always controversy as to whether to say an FIR system because you're saying F, or a FIR system because it's a, and that the F actually stands for finite. So I'm going to say an FIR system. Operates on inputs in what I like to call a sliding window fashion. And this terminology pervades signal processing communications. You see it all the time. Sliding window this, sliding window that. Why do they call it why do these things process inputs in a sliding window fashion? Well, say you have a causal FIR system governed by that kind of an equation. The prototypical I/O relationship. And you visualize the input signal as, you know, x, say x of dot, 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 say x of -7, x of -6. This is going to get a little tedious here. X of -5, x of -4, x of -3, x of -2, x of -1, x of 0. And darn it, you know, I don't have enough board to do this. So let's not make them minus. Let's say, let's start it earlier, start it later. X of -3, x of -2, x -1, x of 0, 1, 2, 3, 4, dot, dot, dot. OK, so that's, think of your input values as lying in a line like that. Now, suppose I want to compute, suppose m equals, say, 4. And well, make it m equals 3. How about that? M equals 3. And you're looking at one of those systems. So you have y of n equals sum from k equals 0 to 3 of bk x of n minus k. If I want to compute y of, say, 0, what do? I take x of 0, x of -1, x of -2, x of -3, plug them into this equation, and get y of 0. So the values here, in between here and here, are, you use these to find y of 0. Get it? I just want to make sure everyone gets that. How do I find y of 1? I need to look at x of 1, x of 0, x of -1, x of -2. So these values in here I use to find y of 1, right? See that? And if I want to find, say, y of 4, I use these values. So what's going on here? What I'm doing is essentially I'm taking a window of length 4 and sliding it along the input values. And to compute the value of y at the time corresponding to the right-hand end of the window, what I do is I look at the values of x that lie in the window, and I manipulate those according to the bk equation. So essentially, for each n, you compute y of n by taking a linear combo with the coefficients being the bk's, the taps of the tap delay line, a linear combo of the input values that lie in a window of length m plus 1. Remember, it's not just m because you have m plus 1 terms in that sum, whose right-hand end sits at time n. Whose right-hand end sits at time n. And to get future y values, just slide that window along to the right. That's why these systems operate in a sliding window fashion. All right. Now, there's some terminology that turns out to be useful when discussing these FIR systems. And there's one piece of terminology where the book and I disagree, and like I told you, yeah, Eric.
So before we mentioned that our output y of n depends on the entire signal x, so in this case, are we saying that it's none not dependent on the whole signal, but just a subset?
Exactly. Okay, let me repeat what he said, okay? Earlier, I said that system notation is a little bit deceptive because in general, the value of the output at any time n can depend on all the input values. However, for an FIR system, that's not the case. The output at any time n depends only on a restricted set of input values. And for these causal FIR systems, it's the values in the window of length n plus 1 that has right hand n at time n. Those are the values of x of n that y of n depends on for each n. And in some sense, you can think of a lot of system properties, FIR-ness, causality, whatever, and we'll talk about some of these some more later, as just restrictions on how the output can depend on the input. Like causal systems are going to be ones for which the output at any given time can't depend on the future. It can only depend on the past. But anyway, yes, that's exactly the case. All right. All right, so here's some terminology. And the universal terminology is, for this, we say a signal x of n has finite duration. What does it mean for a signal to have finite duration? It means that there exists n1 and n2 such that x of n is equal to 0 when n is less than n1, and x of n equals 0 when n is bigger than n2. So you can think of a finite duration signal as one where there's like an on time and an off time. And the only place where it's allowed to be non-zero are n values between n1 and n2 inclusive. So that is to say, the only n values where x of n is allowed to be non-zero are n1 less than or equal to n less than or equal to n2. And x of n can be 0 for some or all values in that interval. Like we regard the 0 signal as having finite duration. But, so note, x of n is allowed to be 0 for some or all n values between n1 and n2. But it can't be non-zero outside of that. So you can think of n1 in general as an on time, and n2 as an off time. X of n is off before time n1. And also after time n2. That's the way that you would explain it to my nephew, at least. Maybe not your nephew, but anyway. All right, so that's what a finite duration signal is. Now, here's the piece of notation where or piece of terminology where my terminology differs from that of the book. All right, so if x of n is not the 0 signal, so we're not talking about trivial examples. So isn't the 0 signal. 0 signal by this definition will be a finite duration signal. So if x of n isn't the 0 signal but has finite duration, the what I call support interval for x of n And again, there's disagreement about whether it should be of x of n, for x of n. I'm not going to sweat about that detail. Prepositional debate. Support interval of x of n, and you can probably guess what this is going to be. It's going to be like the smallest interval outside of which x of n is 0. So it's taking the on time to be as high as possible and the off time to be as low as possible. So the support interval of x of n is the smallest time interval outside of which x of n is 0. That's what I call the support interval. Now, the book calls this the support without the word interval. So caution. Book calls this, quote unquote, the support of x of n. But that, in my opinion, is not good terminology. Okay, and I'll give you an example of why, in my opinion. Okay, so consider two signals. Consider these two signals. How about x of n, and then we'll take the 3-minute break, because I know we're getting there. X of n is equal to, say, how about 3 when n is between 0 and 4 not inclusive, and 0 otherwise. So this x of n is 0 for time less than 0, 0 for time bigger than or equal to 4, and for time 0, 1, 2, and 3, it's equal to 3. Here's another signal. X of n is equal to, say, 5 when n equals 0 and when n equals 3 and 0 otherwise. Okay? So let's do stem plots for these guys to make sure we're on the same page. Both clearly have finite duration. So here's one of them. It's going to be 0 before time 0, then it's 3 for a while, and then it's 0 after that. So this is -1, 1, 2, 3, 4, 5, 6, etc. That's one of the signals. This is the other one. It's 0, and then all of a sudden it's 5 here, and then it's 0, 0, 0, or no, it's 5 again there, but then it's 0 after that. So you have two non-zero stems. All right, these two signals both have finite duration, both have the same support interval, so both have finite duration. And by the way, finite duration is something you have. It's not something you are. Like if I'm a signal, I don't go around saying I'm finite duration. I go around saying I have finite duration. Okay. Now that may sound picky, but anyway, both have finite duration. Both have support interval. What? Tell me what the support interval of both of these signals is. Just phrase it in a like something less than or equal to n less than or equal to something else form. Bryce?
Just when n is less than or equal to 3.
Well, what about like?
I guess it would be between 0 and 3.
Yeah, it's 0 less than or equal to n less than or equal to 3. Very good. The book would say that they both have support, 0 less than or equal to n less than or equal to 3. But I don't like to say that because in real math, grown-up math, okay?
Real math.
No, the support of this signal is, guess what? It's just 0 and 3. Okay? It's not the interval. So in quote-unquote adult math, and actually that sounds kind of like prurient. So let me call it grown-up math. In grown-up math, the second signal has support, just plain support, the set consisting of 0 and 3. The first has support. Zero, 1, 2, 3, which is the same as 0 less than or equal n less than or equal 3. So that's why I prefer to say support interval rather than just support. All right, so let's take the 3-minute break, and then we'll talk about what happens when you put finite duration signals through FIR systems. All right, so anyway, let's see what happens when you What's everybody talking about? Was there another prelim today?
There was a prelim.
Like last class.
A math prelim? Or okay. Oh, how many people are taking probability this semester? So you just had a prelim in class, is that correct? Right before this. So that's why everyone's all energized. Yeah. Now, when I taught probability last spring, we had our prelims at night because we couldn't fit everybody. I mean, the class was too big to have a prelim in our actual classroom. So we had the prelim at night, and that turned out to be the first prelim. We had a little problem. We had like the different rules in the different rooms. Now, you were in Statler, right? So you had the harsher rules, like to the point where we had to I computed the mean and the median for both rooms, one of which was Ives. This was in the dead of winter, so it was freezing cold, and I was going back and forth between Ives and the Statler, and it turned out it was a disaster. But anyway, everyone lived through it, right? Everyone. What happens when you put a finite duration system through an FIR, in particular causal FIR system? So let's look at what happens. When you drive, and this, by the way, is standard systems talk. You use the word drive to mean use as input, whatever. When you drive a causal FIR system with a finite duration input. Signal. And to do this, I think it's useful to look at a really specific example of causal FIR system and really specific finite duration inputs. And so how about we use those two inputs, those two signals above, as inputs to an averager system that looks like this. Say y of n is equal to 1/3 sum from k equals 0 to 2 of x of n minus k. So this is like a threefold averager. Okay. Causal. Threefold averager. Whatever that means, we'll get to that later. So what does this do? The value of y at any time n is the average of the values, the previous three values of the x's. Think of it as a sliding window kind of operation. You have a window of length 3 that you're sliding along the input signal, and you average the values of x of n in that window to get the value of the output at the right-hand end of that window. So let's drive the system with the little pulse of 3s and see what comes out. So let's use so drive with the x of n is equal to 3, 0 less than or equal to n less than or equal to 3, and 0 else input. You get what for your output? And what I'm going to do is I'm going to encourage you to think, again, think of the way the system is processing the input as sliding a window along and doing something with the values of the x in that window. So I'm going to walk over to that picture here and say, OK, so what is y of n when n is less than 0? When I drive the system with this input? It's 0. How come? Who said that? Critique. Yeah, I have a window of length 3, and I'm sliding it along. And the right-hand end of the window is where the n value of y I'm trying to compute is. And for n less than 0, that window contains only zeros. Taking the average of them gives me 0. So y of n equals 0 for n less than 0. So you think sliding window. You get y of n equals 0 when n is less than 0. That's the first step. All right, now, as soon as n hits 0, boom, all of a sudden I have a 3 in there, right? So what's y of 0? What is y of 0 going to be? OK, some people said 3, some people said 1. OK, how many people think 1? How many people think 3? Done you? Oh, never mind. Can't back out now. No, it's actually 1 because it's not a running summer, it's an averager that I'm looking at here. So you have a window of length 3. It has 2 zeros and a 3. And you take the average of those, so 1/3 times the sum of those is 1. So y of 0 is 1. Y of 1 is going to be what? 2. Y of 2 is going to be what? 3. Yeah, so y of n is 0 when n is less than 0. Let's build this up. Y of 0 is equal to 1. Y of 1 equals 2. Y of 2 equals 3. And then the window starts setting in the east. The windows go the opposite of the sun. Okay, so the window is sliding across like this. Y of 4 is actually also going to be 3, right? So y of 4 is equal to 3. Wait. Y of 2 is, I did something wrong here. Y of 2 is 3, y of 3 is 3, y of 3 is 3. Y of 4 is going to be 2 again, right? Because, no, it has 3s, 3 in there. Y of 4 is going to be 3. Then y of 5 is going to be 2. Y of 6 is going to be 1. Why is that the case? I'm doing this wrong. Yeah, I turned it on. Wait. All right, let's start again. 1, 2, 3, 3, 2, right? Yeah, 1, 2, 3, 3, 2, 1, 0. And y of n is 0 for n bigger than 6 as well. See how that works? You're sliding the window along. And if we did a stem plot, let's not be subjunctive about it. Let's do it. So here's a stem plot for y of n. Y of n is equal to, and it's going to be out of scale, so this is going to be 3. Or, no, 1, 2, 3. And then there's 2 3s in there, right? 3. And then a 2, and then a 1, and then a zeros after that. So this is what the stem plot for y of n looks like. Now, here's a general property of FIR systems. They tend to smooth out inputs. Okay. Yes.
Shouldn't the values be divided by 3 since it's an average? It's an average. Or with y of n is equal to 1/3 become the 3 values.
Yeah, well, there's the values are 3s.
Oh, I'm sorry.
Yeah, no problem, no problem. Yeah, yeah. Values are 3s. Okay, so this is 2, 3, 3, 2, 1. Okay. FIR systems tend to smooth out inputs. So here you're taking an input that's like a rectangular discrete time pulse. Like if you took your contacts out or your glasses off or whatever, you would see it would just look like off, and it's on for a while, and then it's off. Now what comes out of it is something that ramps up and ramps down. Okay, so this is like a smoother version of the input, and it turns out to be a common feature of these systems. Let's see what happens when we drive. First off, notice that y of n has finite duration. And what is its support interval? What is the support interval of that discrete time signal, that finite duration signal? 0 less than or equal to n less than or equal to 5. Yes. Very good. Okay. Now let's drive the system with the other one, the Twin Towers signal, and see what we get. So for the other input, signal, again, you're going to have y of n is equal to 0 for n less than 0. And now what happens when your window, remember, you have a window of length 3, sliding it along, boom, all of a sudden it includes a 5. What's y of 0 going to be? I heard it. 5/3. Yeah. Y of 0 is 5/3 because it's the average of 1 5 and 2 zeros. Y of 1 is also 5/3. It's the average of 1 5 and 2 zeros. Y of 2 is also 5/3 because it's the average of 1 5 and 2 zeros. Y of 3, also 5/3. Right? Same thing, same thing, all the way out to 5. So y of n is equal to 5/3 between 0 and 5 inclusive. And then as soon as you hit 6, it's 0 again. So y of n is equal to 5/3 when 0 is less than or equal to n, less than or equal to 5, and y of n is equal to 0 for n bigger than or equal to 6. So here's a stem plot of this y. So this is times 0, this is time minus 1, minus 2. So at 0, it's equal to 5/3. And then again at 1, 2, 3, 4, 5, and then boom, it's 0 after that. All right. So again, your y of n has finite duration. And what is its support interval? Its support interval is the same. It's 0 through 5. And it is arguably a smoother version of this double spike. You know, you have a double spike, and you put it through the averager, you get a pulse. If you put a pulse through the averager, you get a ramp and a ramp, you know, things like that. So the general feature of the smoothing property of FIR systems that these examples illustrate, and also this business about finite duration goes in, finite duration comes out, is in fact a general property. So here's a general fact. If you drive an FIR system with a finite duration input, So if x of n has finite duration, and you use x of n as input to an FIR system, for a minute I had this uncomfortable feeling that I was erasing something I just wrote. And this comes from my other class. And one of you is in that other class, right? Yeah, you're here, right? Yeah, we have these boards over in Thurston where every now and then I have like done a board error and forgotten to flip the board, you know. So anyway, but it can't be done in this room because the room, this is just a nice finite duration set of boards, whatever. If x of n has finite duration and you use it as input to an FIR system, the output that results will have finite duration. So finite duration in, finite duration out. And in fact, you can figure out the support interval in general, and it's not going to be perfect in the sense that it's true every time, but in general, the support interval of the output, so generally speaking, and we'll put some more numbers on this later. I'll just say generally without the speaking. Generally, the support interval of the output is going to be like the sum of the support intervals of the input and the length of the FIR system as characterized by n. And let me put it this way. We'll have length equal to the following. M plus the length of the support interval of x. And there might be a -1 there. I always forget. So let's see. M was 2. No, there's no -1. So for our examples, this works out, right? Because each of these x's had a support interval of length. What was it? 4? Is that right? Yeah. Each of the x's of n, or x of n's, whichever the correct plural of that is, had support interval of length 4. M, for the threefold averager, was 2. 4 plus 2 is 6. And sure enough, boom, 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 boom. You have 6 non-zero values for each of those things. So we're going to be able to get more quantitative about this later on. We talk about convolution of finite duration signals, but that's the general fact. You know, you have finite duration input in, finite duration input out, and the lengths of the support intervals of the b's and the x somehow add. Okay, so more on this later. Okay. All right, so that's just an example of sliding window thinking and how it enables you to figure out what's going on with these systems, and that's important. So now for some special signals, some special discrete time signals that come up a lot. So here's 2 special signals that come up a lot. And these signals we're going to have fixed notation for them that we use for nothing else over the course of the semester. One of them is the discrete time unit impulse. And how many folks have seen, like, had a course where you talked about, like, continuous time unit impulse, Dirac delta function. Where are you seeing that?
Diffie Q.
Diffie Q. So, okay. So you've seen it in Diffie Q. How about other people? Have you seen it in other courses? Have you ever seen it in like circuits? Do they do it in circuits anymore?
Oh, yeah.
Kind of.
Step functions and circuits.
Okay, we're going to have those too.
Yeah. Like that, it was just like, oh, like when you turn on an analog
Yeah.
signal, like you can kind of treat the transient like a step function.
Yeah, we're going to see that all that stuff, the transient stuff, steady state stuff, that's going to come up at discrete time as well. You know, but yeah, turning something on is kind of like multiplying unit step times for everything.
Yeah.
But the thing is, in continuous time, as Alec probably remembers from Diffie Q, the unit impulse was kind of an ugly thing. It wasn't really a signal. You know, it wasn't really a function. What was it? It was like infinity at 0 and 0 everywhere else, but it integrated to 1 all the time. You know, how, you know, what even is that? Okay. Unlike that animal, the discrete time unit impulse is an actual discrete time signal. Okay. It goes like this. Delta of n is what we're going to use notation for it, is equal to 1 when n equals 0 and 0 otherwise. So stem plot for a delta looks like this. It's 1 when n equals 0 and 0 otherwise. These are all 0 stems. So on. It is, unlike the continuous time unit impulse, it's a true signal. And that's comforting. It makes the math easier in discrete time than continuous time. All right, that's one signal we're going to use a whole lot, and the other one is the discrete time unit step. And for that, we reserve, for exclusive use, the notation U of n. U of n is 1 when n is bigger than or equal to 0 and 0 otherwise. So a stem plot for this looks like this. It's 1 to the right of 0, including 0. And 0 to the left. And because we're talking discrete time, there's no kind of like awkwardness about what happens at n equals 0. It's unambiguously 1 when n equals 0. Those are two really important signals. And notice that you can write the delta in terms of the u. Delta of n equals u of n minus u of n minus 1, right? If you shift the u of n to the right, you just get a step that starts at 1. And if you subtract that from the standard step, that cancels all these guys and gives you a delta. So that's something that is actually useful once in a great while. So I'll note it in passing. So note that delta of n is equal to u of n minus u of n minus 1. And this is a kind of a discrete time version of a mantra you might have been taught to recite at one point, which is that the Dirac delta is the derivative of a unit step. Have you ever heard that one? Did anyone ever say that to you? Yeah, kind of. So right. So there you go. That's a discrete time version of that. All right. So those are two important signals. What happens when we drive the causal? We drive the threefold averager, say, with a delta. What do we get? Well, you could do that. You could say it's 0 for n less than 0, and you come up. Once you hit the 1, you get 1/3. And you get 1/3 again, you get 1/3 again, and then you get zeros after that. And if you drive with a unit step, you can see what's going on. You get zeros up until 0, then you get 1/3. This, by the way, is 1. Then you get 2/3, then you get 3/3 after that. So for the averager system, y of n equals 1/3 sum from k equals 0 to 2 of x of n minus k, driven by these. What happens when you put a delta of n? Delta of n goes in. I'm going to represent this schematically. What comes out is this signal. It's 0 for n less than 0, and then it's equal to 1/3 for a while. Not very long. And then 0 after that. Unit step goes in. And if anybody doesn't see why these are the case, I saw a couple of frowns out there. Maybe because it looks at his watch to see if I'm going over time, right? I'm going by that clock, which is like 1 minute slow. Haha. So sorry, guys. This is the last picture I'll draw.
Replaced the battery on Friday. So
Oh, really? Oh, by the way, have the mic batteries worn out yet?
one time.
One time? So that big package I got at Stop and Shop is in Massachusetts still good?
Yeah.
Yeah, OK, cool. I had to go buy batteries for this mic because the department wouldn't buy it for us. So, you know, I roll, you know. All right. So 0, minus 1, minus 2. Then you have 1/3 and 2/3, and then 1 after that. Forever and ever and ever. So again, a step gets ramped. It gets nice smoothed out. A spike gets pulsed. It's a smoothing property. So now you have practice doing these things a little bit. And next time we're going to talk about impulse response, convolution, all that kind of good stuff.